what's this week's going to be? I was right, someone turned up. And we're going to be doing hypothesis testing. Chapter 12 is going to be hypothesis testing with proportions, right? 42% said this and so on. And chapter 13 is going to be a hypothesis test with means. So we're going to look at how do you prove that there's enough evidence that something is true or not true. And there's a lot of structure to these things, a lot of notes. I've got some of them here, and I will refer to them and point at them. But essentially, let's take a kind of overview. In science and in medicine and pretty much any physical or medical science, there is a problem of how do you prove something? Now, it might seem like a pretty straightforward thing, but in many cases, it's quite difficult to prove something if all you relied on is your data, right? So you've collected data and you said, see, this proves X, Y, Z. And somebody else will look at that same data and they'll say, nope, that doesn't prove a darn thing. And you know, you can imagine a pharmaceutical company have a new pill and they do a clinical trial and they come back and say, see, our new pill does better than the old pill. And someone else says, no, it didn't. You know, how do you formalize proving something? So it's going to sound, and it does to me at least, like a lawyer got involved here. So when we prove something, we use what's called typically, it's called a hypothesis test. This is a major tool used by many scientists to prove something. It's a formal way of setting out what you're trying to prove. Then you provide evidence for it, and then we do some statistical analysis. And from that statistical analysis, we will be able to then say, yes, you have proved what you said you wanted to prove, or no, there's not enough evidence to prove what you just said, right? Okay. The analogy that they use an awful lot, and it's quite a good one, so don't worry about not getting here yet, is a criminal trial. There are going to be two hypotheses, only one of which can be true. And so H naught is that, what we call them? I'll just call them a person. So somebody's on trial for murder, and H naught is that the person is innocent. And the alternate would be that the person is guilty of the crime, right? And that's it. You're either guilty or you're innocent, right? That would be the dichotomy, right? So my theory is correct, right? My new theory is proved to be correct, or my new theory is not correct, right? Well, we don't actually do quite that in a court case, although you might think it is. If you get a verdict, a verdict is basically your decision, right? So the decision, that's how you spell it, but whatever. There are two decisions. One is the jury says you were guilty. And the other says you are not guilty. And a lot of people think that not guilty in the criminal system means that you're innocent. Can't not guilty just mean there wasn't enough evidence to prove that you did the crime? Would you agree that there's some famous crimes out there that the huge majority of the population says, yep, you did kill her, but there wasn't enough evidence to prove that you killed her? So that's why it's called not guilty, right? So we're going to deal with two hypotheses, two theories. One is called H naught, and that's called the null hypothesis. And actually, let me use my notes now. The null hypothesis is always to do with the proportion, right? So the proportion of Americans who have been to Canada is 35%. And the other theory is that the proportion of Americans who's been to Canada is less than 35. So you're either it is 35 or you're less than 35, right? So there's your two. You can't be both, right? You're either is 35 or it's less. And we call this the null hypothesis, and we call the opposite event, in this case, this one here, the alternate. And then if you want to put this in English, if you believe that the proportion of the population has a p-value that's now less than 35, that's how you would do it. So can you imagine somebody was thinking, you know, the last time we measured this, 35% of Americans have been to Canada. I think with this COVID, it's actually not as much anymore, right? I think it's gone down. Well, this is how you would set up your hypothesis. It is 35. I now want to prove that it's gone down, it's went less. Different story. Imagine 35% of people like Pepsi, or at least that's what everybody thinks. And you think it's a lot more than that. So your null hypothesis would be percentage of people who like Pepsi is 35. Your alternate is, I think it's bigger than that. And we call these one-sided tests because you've got an equals and a less than, you've got an equals and a greater than. The null hypothesis is always going to be P equals some number. It's the number that everybody thought was true and maybe still is true. And then the alternate is going to be, nope, I think it's less than that. Nope, I think it's more than that. And the third possibility is, I don't know what it is, but I'm pretty sure it's not 35 anymore, right? It's changed. And that's a not equals to. And when you've got that one, it's called a two-sided. So if you believe, got to make my V's look better. If you believe something is changed in some way, but you're not 100% sure how it's changed, you would do this version. So one-sided, one-sided, two-sided. Now, can you see that? Doesn't that sound to you like they got a lawyer involved? That you write it down in terms of, a hypothesis is just a fancy word for a theory, right? My theory is that it's 35. Well, their theory, right? Everybody else's theory is it's 35. My theory is that it's less than that, right? Everybody believes that their theory is it's 35. My theory is it's bigger. You believe it's 35. My theory is it's not 35. And these are the only three kinds of hypothesis tests that there are. And one of the things to kind of notice is the null is always P equals somebody. And the alternate is either you believe it's actually less than that number, more than that number, or not equal to that number. There we go. Now we're doing big picture stuff here, so there's no real calculations yet. The next fella. Okay, so you make your hypothesis test and you set it up. There is two possible kinds of error that could happen in a hypothesis test, and they're called a type 1 error, and the other is called a type 2 error. A type 1 error is when you come to the conclusion that your alternate hypothesis is true. In other words, see, I was right, I proved it. When in fact you were wrong, right? You said, look, I've proved it. Now you might say, well, if you proved it, then that must mean it's true. Well, that's not real life. Couldn't you just get really lucky data that made you think it was true and you got enough evidence to say it's true? Analogy. When I tell you it's a 99% confidence interval, right, and I use that to prove something's true, isn't there a 1% chance I'm still wrong? right? 99% confidence interval. Isn't there a 1% chance the real answer's not there? That's a type 1 error, right? The 1%, right? The bit that's, you know, you're going to always be in real reality world situations. There's always going to be a less than 100% on anything, right? There's always an error. You could just get it wrong. Now, what would a type 2 error look like? Well, this is when you make the conclusion that the null hypothesis is true when in fact you're wrong and that the alternate hypothesis is true. So this is where you end up saying, my theory wasn't right. Right. The evidence actually is pointing the other way. It was 35 all the time, right? You went that road. And darn it, you were wrong. Your evidence wasn't good enough, but it didn't mean that, you know, the underlying truth was different. So these are called type 1 error, and these are called type 2 error. And there's got about 20, that's an exaggeration, there are about 5 different ways of phrasing both of these. So you'll see as we go through some of the homework questions, all the different ways they phrase type 1 and type 2. Off the top of my head, a type 1 error would be when you rejected H naught when HA was true. That would be another way of saying it. Or you failed to reject H naught when HA is true. Or you did reject H naught when HA was false, and all those other weird combinations. Thankfully, there's not many questions that do that, but there are some. So we've got the idea that there are 2 possible theories. One's called the null hypothesis, and there's the one that you're hoping to prove, the alternate. And there's 3 versions of that. And in each one of these situations, there are 2 possible errors, right? This type 1 is you got it wrong for that reason. Type 2, you got it wrong for the other reason, right? But whatever it is, you got it wrong. Getting things wrong are bad. Still on the big picture, but eventually we're getting to the point where we can actually do some numbers, which is what that question is going to be. Is that for every hypothesis test, we go looking for a number. And this special number is called the test statistic. And what this test statistic is going to do is based on its value. If it's a really big value, that means, hey, I've got evidence to prove what I think was true, right? The alternate is true. And if the Z's value, this test statistic is called a Z value, if it's small, I don't have evidence, right? Do you know the Z value? The Z is not a coincidence. It's actually essentially a Z score, but it's called a Z value. Oh, can anyone tell me what number the Z score should be to be big, to be like outlier big?
What kind of Z?
Ooh.
Far away.
1,000 is definitely true, but 1,000 is actually a way much bigger than you need. Can you remember 1, 2, 3? Can you remember Z scores? How big does a Z score need to be an outlier?
More than 3 or less than 3?
More than 3 or less than -3, right? That's the kind of, that's what the Z score does. It's like a number, like a sliding scale. And the bigger it is, the more sure your idea, right? Your alternate hypothesis, your alternate theory is going to be correct, right? Z big scores are good for you, right? Now, to calculate the Z value, it's the sample estimate, take away the null value, divided by the null standard error. We're going to put that into an equation later. My null hypothesis will look like P equals some number P naught. P naught is called the null value. Our alternate hypothesis in this case is greater than. The sample estimate is what we got in our sample, and the null standard error is this guy. So this here is going to be the number crunching that we will deal with. So let's put it out the way. So here's my story. It was known in the year 2010 that the proportion of French adults who are obese overweight was 0.19, right? So 19% of French adults were overweight. That's the general held belief by all the people who are interested in that data. And you're a research scientist, and you've got a gut feeling that this has changed, right, in the last 12 years, right? COVID has made people fat, right? Because they're sitting in the house, they didn't have anything to do, they eat, stress eating, whatever. He's got a good feeling that that has now changed. So he conducts a hypothesis test to see if there's any evidence to support his theory. So what he did is he collected a sample of 400 French adults, right? A good random sample. And you know that BMI number that they decide, you know, if it's bigger than this, you're overweight. And he found out that 22% of his sample was overweight. Okay. The null hypothesis is that the percentage of Frenchmen who are overweight was that number, right? We call that P naught. Its name is the null value. In this story, he believes it got bigger. So we're doing a P greater than 0.195. Are you comfortable that for his story, the null hypothesis is what everybody thinks it is, and the alternate is what he believes is true, right? He believes it's got bigger, right? That's a one-sided test. Now, the next thing we do is calculate the Z value. Now that formula that I have over here, I'm going to rewrite it in a much more simplified version. Isn't it a lot nicer when you see it that way? Does that look more like a Z-score to you now? Now, at the side, we're going to calculate the standard error of the sample. It's the square root of P naught, 1 takeaway P naught over N. A lot of people make the mistake of using that number and not this number. Remember, this guy here, that's the P naught. So it's going to be the square root of 0.19 times 0.81 divided by 400. .19 times 0.81. I forgot to put that in a square root. Let me do it again. Square root of 0.19 times 0.81 divided by 400. And we get, don't need that anymore. We get 0.0196 and plenty other digits. So our Z value is 0.19, take away, that's a P hat, which is 0.22, divided by 0.0196. Right, so sample, P naught, standard error. Put that into the calculator, and we got 0.19, take away 0.22, all divided by 0.0196. And we have the answer, negative 1.53. Now, remember we went and said bigger than 3 or less than -3, that's not big enough, is it? So what we would say here is that we've not enough evidence to prove this is true, right?
I have a
Maggie?
question.
Yes.
So why did, when you were plugging in the values to find the Z value, why did you switch the P hat and the P no?
I did? Oh, because I made an oopsie. And now it's positive 1.53. Yeah, I don't know why I did that. Careless. Is 1.53 not big enough either? Agreed. And so what the conclusion we would make here right now, and we're going to refine it in a little while, is that we'd make the conclusion that there's not enough evidence to prove that this alternate theory is correct, right? What that's saying is you could easily have got this data with that percentage being true just by the randomness, right? Couldn't you just get a few extra fat Frenchmen when you were weighing them, right? Could happen. Not that exceptional. Now, if this Z value had been like 3.89, right? Can you imagine it was that? This would be evidence. So you would be able to say, I've now proved that Frenchmen are actually heavier, right, than they were 10, 12 years ago. Here, all we say is not enough evidence. We don't actually make that a positive statement. We don't say, we have proved that it is still 0.19. All we've said is, not enough evidence to prove what you wanted. Right, and that's it. This 3 that I gave you, right? The Z-score of 3 rule, right? It works, but it's not refined enough. So what they go, and we're going to show you, Salt does all this, thank goodness, because it's really messy if you had to do it by hand. But I'll kind of show you how it would be done once by hand. After you get the Z value, the Z-score, you then get a thing called the p-value. And the p-value is the probability that you get a Z-score, in this case, greater than 1.53. And that you would do on Salt. And I'm trying to find, you can bear with me for a minute. Let's load that thing up and I'll show you where you would find such a thing in Salt. I think that'll do. As I say, what I'm showing you by hand is kind of doing it once by hand, but really Salt is the best way to do it if you can. Right, so you should be looking at chapter 12 right now. Are you guys? Is there a Salt button on this one? Of course not. Why would they? Why would they be nice to me? Okay, then I will go to the settings one, which I know will have it. There we go. Yay, there we go. Using Salt. Now, normal distribution, totally fine with that. I want to know the chances that I get a Z value greater than 1.53. So hit the right tail, that's for greater than. Keep those guys the same. Change this number to 1.53. And the answer you get is that number there. Do you see the guy at the bottom, 0.06? That's the p-value. Let's now return, continue this process just a little bit further. The p-value is essentially the probability that you got your Z-score. Can you see that I could have got that Z-score about 6% of the time just by randomness, right? Can happen, 6%. So how do we decide, in a more general way, how small does a p-value have to be before it's not just coincidence, it's really evidence, right? Well, we have another guy, another guy called alpha, and he is called the significance level. Every hypothesis test has a significance level attached to it. There are 3 significance levels that are typically chosen. That's the 10% level. That's a 5% level. And there is a 1% level. By the way, this alpha is your type 1 error. So if I choose this one, my conclusion will be wrong 10% of the time. So if I say something and I've proved it, well, 90% of the time I've proved it and it's right, but 10% of the time I'm going to be wrong. If I use this one, it's 5%. If I use this one, it's 0.1%. This p-value is the percentage of the time, right, I would get it wrong essentially as well. That's another way of looking at this. So what you do to finish this is you do a test. And the test is the p-value that you calculated, is it less than the significance level alpha? And it doesn't matter if you're doing prove that it's bigger than, prove that it's less than, prove that it's not equal to. It doesn't matter. It's still the p-value has to be less than the significance level. So let's pretend that we chose this significance level. Then I would be saying, is my p-value less than, is my p-value less than my significance level? And the answer is no. And that's why I haven't enough evidence to prove it. Well, I haven't enough evidence at the significance level of 5%. But suppose I decided that my significance level was going to be 10%. In this case, the answer would be, yep, you've actually proved that Frenchmen are in fact fatter now than they were 12 years ago. Now you might say, well, how can you prove something that's not true and then later on tell me you can prove the same evidence that it is true? It's all to do with the significance level, right? If I only wanted to be right 50% of the time, couldn't I make my alpha 50%, 0.5? And wouldn't I get it right half the time? Right, I'd say, hey, I proved it's right half the time. Half the time I'd definitely be wrong, right? Can you see why this part of the puzzle is fraught with danger? If you're a scientist and you've spent 20 years of your life trying to prove whatever it is you're trying to prove, isn't there a big temptation that you want to pick a nice big significance level so that you can publish your paper and say, I have proven that blah, blah neutrino interacts with blah, blah alpha waves, or whatever it is you're trying to prove? Because if you try and use it with that one, you might not get enough evidence. And if you try and use it with that one, would you agree you probably would very, very rarely get evidence? But if you're thinking of confidence, isn't this a much more confident conclusion if it works here than if it works here? Because at least here, you're only going to be wrong, what, 1% of the time? I don't feel comfortable about 10% of the time. So which one you choose depends on circumstances. If I'm interested in have Frenchmen got fat, I could live with a 10% chance of being wrong. What damage am I going to do if I say they're fatter than they're not? I've insulted some Frenchmen, right? That's about the worst, right? Now, if I'm a pharmaceutical company and I'm wanting to prove that my drug is better than the old drug, can you see that getting that wrong could be dangerous? I'm putting out a new heart medication that I tell you is going to do a better job than the other one, and it doesn't, right? Well, if I use the 10%, isn't there a 10% chance that that's exactly what happened? The new drug isn't any better, might even be more dangerous. Bad news. So can you see in the pharmaceutical world, won't you want to be on this side of the spectrum, right? Now, if you ever see papers where they've done different experiments at different places, and I've used a 10% here, and I've used a 1% here, and the other 4 times I did a 5%, that is cherry picking. You can tell that a mile away, because if that theory was true, wouldn't it be 1% all the time or 5% all the time? So you know when you're switching, aren't they saying, oh, it's not going to work on a 5, but it will work if I use a 10? You can see that, you know, when your p-value is 6% kind of story. So if you ever see papers where they jump around, that's what they've done. Right. Now, there are a lot of number crunching going on in this process. So let me show you how to do one using salt from scratch, right? So we need to have a theory that we're going to try and prove, right? So what shall I pick as my theory? You do not know this because I've just made it up, but 25% of Germans drink a lot of beer, right? 25% of German adults drink a lot of beer. A lot of beer is more than 5 pints a day, right? I made that number up, right? So we've got a lot of drunk Germans. You actually think that it's even worse than that. So your alternate hypothesis is, it's not 25%. I know, because I walk about Germany and I see a lot of drunk Germans drinking beer, and it's more than a quarter of them, right? Like every second person is drunk, right? You can tell this is totally made up data, right? But we've got it. Now you have to prove that. So you're going to have to set up some information. You took a random sample of 300 Germans, and you found out that you got 29% of them that you interviewed, whatever you want to call it, were drunk, right, on beer. Now comes what significance level we should choose. Now, isn't that it depends on context, unless the question tells you, right? Do you think in this story, it's not that bad if I get this wrong? And because I don't think it's that bad, I'm going to use the 10% significance level. So I've got my null alternate set up, and I got this guy, right? All the data plus my significance level. And these things should really be done before you do any analysis. So I don't wait until I've got my answer and then I change that, right? That's cheating, that's cherry picking. So let's jump over and show you how you get salt to do it for you. Right, so I'm going to go up here. I'm going to click that fella. Now, the one I want is a proportion, so one sample proportion. Okay, the number of successes, I'll tell you how many that is. 300 times 29% is 87. So there was 87 drunk Germans out of the 300 that I talked about. Now, our null hypothesis goes here. Our null hypothesis was 25. You see it fits in that box there. H naught, P is 25. Now, what is our alternate? Now, here are the choices. Was I trying to prove that it was different from 25, that it was bigger than 25% or less? What was my story?
It's greater.
So I think it's bigger, right? Now, one sample, how many were drunk out of 300? Make sure it's hypothesis test. The null hypothesis goes there, right? So if it was 40%, 0.40 would go there. The alternate is just greater, less than or not equal to, and you hit generate results. And it tells you pretty much everything that you need to know. There's the null hypothesis, and there's the alternate. Isn't that nice that they called it? Remember that Z statistic, that Z value that we were calculating? There it is done for you. There's that P value, which is the guy that we are writing. So I'm going to write that, fill it down. And the P value that we got is 0.054 and some stuff. 548. That's all we need. So let's return and see if that's evidence or not. Right. That's what SALT gave us. So here is our test. Is our p-value, that guy, is it less than our significance level alpha? And we had 0.0548. Is that less than that number? Yeah, it is. And if you get the answer yes, haven't you proved what you were trying to prove? So we have proved, or let's phrase it a little bit more formally, we have evidence to prove that Germans are drunk more than 25% of the time. And the advantage of this rather formal way of doing it is this has been the agreed scientific method. In other words, a German would be looking at this data and said, yeah, it's conclusive. Evidently, we drink too much, right? And you can use this technique for proving that something has changed, right? Bigger, less, or not equal to. And the context can be anything. It could be drinking beer, new medicine, right? Crime rates, who's going to vote for who in the next election, all that kind of stuff. So let's do, for my next one, let's do a story on, can we predict who's going to win an election, right? It's a very common usage of this. So the null hypothesis is 50%. And the alternate is, I think my guy is going to win, right? So do you see 50% is just break even, right? In any election, it's always 50%, right? But I think my guy is going to win the election. Do you see that 0.50 bigger than? Because that's all you need, isn't it? More than 50% vote for you, you've won the election. So how am I going to prove that? Because I think it's true. Well, I go out there and I get a company to Gallup poll or something, right? I pay them money and I say, okay, do a poll for me, find out if my guy's going to win, right? And they normally ask more than 1,000 because of non-responders. The magic number is actually 1,000, but you can't guarantee 1,000. Aren't you going to get 5 or 6 people? Nah, I'm not telling you, go away, right? We don't like that. So you have a few extra just to make sure. And of course, sometimes you end up with a bit more than 1,000 because of that, and that's totally fine. So don't be surprised if you see the real data that that's a weird 102, you know, something like that. That's the only reason for it. Now, of all those people that they asked, 519 said, yep, I'm voting for your guy. I like him. Now, we have to decide on a significance level here. Anybody want to throw one in? There's no right or wrong answer to what significance level to choose. It's how willing are you to be wrong, right? So 10, 5, or 1%, would you want to go for? 5% gets it. Okay, got it. That's the kind of middle of the road, right? It's not as severe as 1%, but it's not as easy as a 10%, all right? So whatever conclusion we come to in the next few moments, isn't there a 5% chance that it's just the wrong conclusion, right? We just got it wrong. We're going to have to live with that. That's one of the frustrations and the beauty of statistics. You know, in equations, x equals 2. And a million years from now, the solution is still going to be x equals 2. But in statistics, we say x equals 2, but I'm only 95% sure that that's right. And I could have got it wrong, right? But if I do another equation, I might get that one right, you know? So 95% of the time I get my questions, that sounds about like me, doesn't it? 95% of the time I actually do it right, and 5% I screw up somewhere, right? So we got everything that we need. So let's nip over to salt. One sample proportion, right? Right now, everything's one sample proportion. The number of successes in this case is people who are going to vote for my guy. And there was 1,007 people here. And this was 50%. Oh, and it was a greater than, right? I want to prove that my guy has won. So I'll generate the results. Oh dear. The p-value is 0.16. Now, the reason I said, oh dear, is I've just spent $10,000 with the Gallup poll company because I'm really sure my guy's going to win. And the p-value that came out was that guy. So when I do my test, is my p-value less than my significance level? The answer is no, which means that there's not enough evidence to prove, you know, that p is greater than 0.50. In my story, to prove that he or she will win the election. Oh, so you just spent $1,000, right? $10,000, whatever it costs to do these things. And the bottom line is, you haven't proved that your guy's going to win. Agreed? But would you agree that there is some evidence that he's probably going to win? It just wasn't strong enough to convict them, right? To guarantee that he's winning, guarantee at least within a 5% error margin at least. Okay. Let's say he phoned up the Gallup poll people and the guy says, oops, we got our 2 digits mixed up. It was actually 591 people who said they were going to vote for your guy, not the 519, right? Do you think that might win? That might be evidence. Still not enough? Let's find out. So It's now 591. Nothing else has changed. And generate the results. Oh, would you look at that p-value? Now, whenever the p-value gets to ridiculously small numbers, in this case, the number is so small that it's less than 0.0001, we will just call it 0.00001. And is that guy less than 0.05? In fact, isn't that guy less than 0.01? In fact, isn't that guy like 1 in a 10,000th chance of getting it wrong? So this one here, right, is basically, if that was true, your p-value is at less than significance level. And the answer is yes. So you can now say there is enough evidence. I'll put it into English this time, to prove that your candidate will actually win. If you are interested, which you may or may not be, politics, when they come to do the midterm elections, which I think is in November, if you stay up and you watch the results, have you ever wondered how come they can say Texas has went Republican, even although there's only 80% of the votes counted? It's because there was so many people voting Conservative or Republican, whatever it is, right? That the p-value was tiny. And so they are really, really confident that the prediction is over with. Now, they are not allowed to do those polls, or they shouldn't be, I don't think they are allowed to do these, on the day of the election. So you're not allowed to do polls on the day of the election. Once the, whatever you call it, the polling rooms are closed, right? Once no more votes are going to be added, then they do it. And I've mentioned this before, it's, remember that suppression of votes thing. Imagine it's a horrible, wintry, miserable night, and somebody unscrupulous decides to do a sample, and they went to a place that was heavily royalist, and they came out with the result, Texas has gone royalist, right? What is a Democrat or a Republican voter probably going to do when they've already been told there's no point in you voting because you've already lost? Can you see how that suppresses votes? Now, even if it's not true, even if the poll I had was totally made up, couldn't the net effect be my guy could still win? Because enough people would have voted for my guy and everybody else didn't bother. So always vote for your guy. And even if he's got or she's got a 1 in a million chance, vote for him. Because don't let the buggers win, right? Because politicians are nasty like that. And I don't trust them as far as I can throw them. And I can't throw politicians that far at all, as you may or may not know. Okay, last name, Bubba.